So let's continue in chapter 4, and in this video we're going to look at sections indicated here through numbers 4 through 7. So we're going to talk about the subatomic particles in the atom, some of its notation, and how some of it's connected to the atomic mass on the periodic table. So I have two slides that kind of summarize the subatomic particles. This one has about its charge and location and things, which we'll briefly go over. The next one has some of the things that we use to help it predict and what I call the subatomic particles job. So that will be the next one. So what's important for us to understand is that chemical properties can be described and predicted based on some of the subatomic particles. While the atom is the smallest form of matter that has chemical properties, it's these subatomic particles that influence these properties. And so we're going to learn a little bit about that. And I also need to point out, as you can see here in the second bullet point, is there are more than 3 subatomic particles known. There's other things like a quark, if you've ever heard, or bosons. And in physics in particular, they really investigate this, trying to understand matter even better. But in chemistry, especially introductory and Gen Chem 1 and 2, having a good working knowledge of the 3 subatomic particles, protons, electrons, and neutrons, help us explain and predict a lot of what we will encounter. So let's look at this table that's from your textbook that is talking about is summarizing the subatomic particles, and let's just go through. So here the first column are the 3 that we're interested in: electron, proton, and neutron. The second column is a symbol, so you don't always have to write out the name. Now I'll just give you my 2 cents about this from your book. So the electron I always see as an E with what we call a superscript negative sign. The proton and the neutron, I have also just seen the proton as a P with no positive and the N with no superscript 0. So just so you know, there's not like a specific rule. I do always see the electron written that way, though. I never see it just as E. But your textbook uses a proton with a superscript positive sign and N with a superscript 0 for the proton and neutron respectively. Now before I go on, here's a little side note, and I find this important to mention just as a part of class, and that is the word that I was using, the words. I'm going to write it up at the top. A superscript, I said, and then there's another counterpart to that, which is subscript. Okay. Now, superscript means, and in class, I know it's a little harder on a video because you can't look at my mouth when I say it, but superscript, all it means is that what you're writing is above the main line of the writing. So, in terms of our symbols there, E with the little negative sign, that little negative sign is written as a superscript. And chemistry is not the only subject that uses subscripts and superscripts. I mean, any kind of writing uses subscripts and superscripts. So that's a superscript. A subscript, the word sub, we're talking about below writing, and we're not using subscripts in what we're doing right at this minute, but if we were to write the chemical formula of water, you notice how we write the 2 below the hydrogen and oxygen. This is called or written as a subscript. So I just wanted to go on a little side here. In class or anytime if I use language that you're not sure what I said, or you're not sure what it means, ask me. Because the more we understand what the words mean, the easier it is for us to understand the concepts that are helpful to us. We don't want to get tripped up on words when we could, if we know what they mean, we could just keep going. So I just wanted to do a little pause there and define superscript and subscript. Okay, so back to the topic at hand, subatomic particles. So we have the three. We have symbols that we can use when we don't want to write out the entire word. We need to know their location. So what you notice is that we're going off the Rutherford model. That's the model that we use. And so the Rutherford model is a nuclear model. And so we see that the proton and the neutrons are in a tight cluster that we call the nucleus. So protons and neutrons are both located inside the nucleus of the atom. The electrons are located outside of that nucleus, and in other sections in this chapter, we're going to learn a little bit more how we characterize electrons being outside of the nucleus. Okay, so you need to know the particles, their symbols, where the respective particles are located. We'll also need to know their relative charge. So protons and electrons have an equal, what we call magnitude of charge, so an equal size of charge, but they're opposites. So electrons are -1 and protons are +1. And it's what we call additive. So if you had 1 electron, it would be a -1. If you had 5 electrons, that would be a -5. Protons would be the same, but they would be positive charge. So one proton is +1, 5 protons is +5. Okay, and then neutrons, as their name suggests, neutrons are neutral. So neutrons do not have a relative charge. It is one reason that they took them a little bit longer to discover them, and that's because they at the early 1900s, they were using charge and how positive and negative interact with each other, and how positive and positive or negative and negative interact with each other to discover things. So it took the neutron a little bit longer. So we need to know their charges, okay? And then their relative mass. Now the mass that they have given you, which I don't like that they don't tell you the unit, but it's in what we call an atomic mass unit. Which can be abbreviated AMU. It's also more modern. They use the unit that's just U. These, for the most part, especially in introductory chemistry, these are used interchangeably. So if you see AMU or U, we're talking about these very small amount of mass, because atoms are tiny atomic mass units. In fact, 1 proton, so you can see here 1 proton equals 1 AMU, which is, I don't remember the coefficient, but it's 10 to the -24 grams. So there's a number here. It's 1 point something, I think 1.7 or something. I can't remember the coefficient. It's not important that I or you memorize. It's the coefficient. It could be in your next level of chemistry. You might have to use this mass more. But for us, we're going to use atomic mass units. But it's a tiny number. That's why I even mention it. It's like 10 to the -24 grams. So you've been in lab now, you know, a -24. That means the decimal, it has 23 zeros before you even get to the first number, this non-zero number. So anyway, it's a tiny number. So they made up a new unit for it, atomic mass unit. And then if you notice the electron, it's even smaller. It's 1 over about 1,800 atomic mass units. What that means, just in different terms, it would take around 1,836 electrons to have the mass of 1 proton. 1,836 electrons have the mass of one proton. And we'll see this doesn't happen. You don't have that many more electrons compared to the protons. And so oftentimes you'll see that I got to think about this. Negligible. Wait, I think I put an extra G in there. Okay, so let me see. Negli. Oh, I got it right. That I have to use my phonics to spell negligible. So sometimes they say the mass of the electron is negligible. And if we were in class, I would say, do you know what negligible means? And what it means is that it's so small that it doesn't contribute, or it's not important to the mass. Now, electrons are super important, but in terms of its contribution to the mass, it is so small, it does not contribute to the overall mass of the atom. It's insignificant in terms of its mass. So sometimes in some textbooks, they don't even include the mass of the electron. They just write that word negligible. That's because it doesn't contribute, because it's so small when you compare it to the mass of the protons and the neutrons. So on this slide in table 4.1, all of this information you do need to have to learn and be able to use and recall and apply to different situations. Okay, so that's important. Flashcards might help you. That's that kind of thing. Now let's look at another slide, still talking about the subatomic particles, and I want to talk to you about their job. And so this isn't from the textbook. I created this just as a summary about some of the important things about each one of these subatomic particles in relationship to what we're going to be learning. So let's start with the proton. So the proton is the number of protons in the atom is called the atomic number. Okay, so protons and the atomic number are the same thing. Now, the atomic number has a symbol you can see there in parentheses as a capital Z. This has to do with the German name for atomic number. It's not someone that's just trying to confuse us. It was named in German, and then English it's atomic number, but the symbol is from the German word for atomic number. Atomic number can be found on the periodic table, and we're going to be talking more about the periodic table. We do not memorize atomic numbers. I'm not going to require you to, but what we do need to know is that the atomic number on the periodic table is the number of protons. Sorry, my brain. I had a pause there in my brain. So the atomic number is the number of protons, and it can be found on the periodic table. And we're going to look more into that as we keep going. The important thing about the proton is it determines the identity of the atom. Okay, so no two atoms have the same atomic number. In fact, that makes me right now want to go, and I have to go through all the videos because I put a periodic table at the end. So here's the periodic table, and the atomic numbers are these numbers right here. So on the periodic table, and we're going to talk more about the periodic table, I think, in the next chapter. But the periodic table is organized or in order of atomic numbers. So see their whole numbers here. And no two elements have the same number, right? There's only one symbol in each box, and each box has its own atomic number. And that atomic number equals the number of protons. Okay, so when I just wanted to get out the periodic table now, just so I could put a visual to what those words are saying. The atoms are organized by atomic number. The atomic number is the number of protons. And we're going to do more with that in this chapter. So don't worry if it's just like starting to settle in, because I have this chapter, you can see as I went through the slides, has quite a few examples. And we'll be looking at what is the atomic number. We'll be using the periodic table. So let me go back. Sorry, I have to. This is not a very modern recording app that I have, but it works pretty well for what I need to do. Okay, so protons, same as the atomic number, and it determines the identity. Okay, electrons. So here's the electron's jobs right here. That's his job. It determines the reactivity and bonding. So electron's job has to do with what kind of reactions and what kind of bonds the atoms are going to form. Okay, so protons deal with the identity. What atom is it? Electrons deal with what kind of reactions are they going to have? What kind of bonding is going to occur? That's what electrons do. Now, how many electrons in a given atom is down here? So for a neutral atom, that's one without charge. And in this chapter, we're not dealing with charge. So everything we deal with should be neutral. In this chapter, for a neutral atom, protons and electrons are equal. So on my example above, lithium right here has 3 protons. How do I know that? Because lithium has an atomic number of 3 on the periodic table. That would mean lithium also has 3 electrons. Its atoms are neutral, so the positive and negative equal each other. Now, neutrons are a little more wide kind of a catch-all thing. First of all, we notice that there is not a specific number, and we're going to do a little bit more with that in some of the examples. So I can't predict the number of neutrons based on the periodic table. I can predict protons, I can predict electrons. Sometimes I can kind of guess at how many neutrons there might be, but we need another number for that, which you'll see here in a minute. But because the neutrons can vary, remember protons and electrons both have one atomic mass unit, but neutrons vary. So ultimately the number of neutrons, the total neutrons will be what finalizes its mass. Neutrons are also associated with radioactivity. In your class, we don't really do anything with radioactivity, but neutrons are involved in that. And then here's another number, and here's another number that we need to remember, and we're going to do some practice with it. So just write it down for now in your notes, and we're going to practice with it. It's something called the mass number. It does have a symbol of a capital A. So atomic number is capital Z as its symbol. So if they didn't write the word atomic number, they could just write a capital Z. And mass number has a capital A. Again, it's based on the German word, and that is why it doesn't match the English word that we have for it. Okay, so it's not trickery, it's just not in English. And so then the mass number, it's a calculated value. It's not on the periodic table. And it's equal to adding up the protons and the neutrons. So it's always going to be a whole number. It won't have any decimals, right? Because you don't have fractions of protons and neutrons. So the mass number and the atomic number, these are always whole numbers. There's no decimals. Now, we're going to learn about something called isotopes, and we're going to do a couple examples to see if we've gotten these definitions and some of how this goes together. Then we're going to learn about something called isotopes, which we're also going to practice some of these definitions. So there's several slides now where we're just kind of trying to apply some of these words and definitions and connections to questions. Okay, so let's try. Oh, I forgot. I forgot. We have to do this one. Okay. backing up, let's talk about atomic notation, and then we're going to try our examples. Sorry. All right, so atomic notation is one way that we can write the symbol for an element that gives us a little more information than just the symbol of an element. So when I say the symbol of an element, it would be like using the letter C for carbon or the letter Mg for magnesium. Now, you should be learning these. I have you learn the first 36 names and symbols of the element. So when I say carbon, you should know that the symbol is capital C. If you see a capital C, you should know that that is the element carbon. And so just a symbol of the element, that's what it is. Now, in atomic notation, or also called isotope notation, they're the same. In this type of notation, we're given more information. Specifically, we're given enough information to figure out how many neutrons are present. So below, I have a generic example, and then we will practice with more specific. So here, I have the, if I look here, put your eyes down here. This is the generic way to write atomic or isotope notation. Okay, so what do we have in this here? On the top here, we have A, which is the mass number. So that's where protons and neutrons are added together. Underneath it, we have Z, which is the atomic number, which is the number of protons. We can find that on the periodic table. And then in this textbook, they're using SY just to mean the symbol. So the symbol, it would be like what I mentioned up there. It would be carbon, magnesium, whatever the letters are for that. So then in the atomic notation, we can not only get an idea about what element it is and what how many protons it has if you know the element. This is also on the periodic table. But we can also discover more about the neutrons. So this is common symbol, especially in nuclear chemistry, but we'll be introducing it to ourselves here. So let's take a look at some examples. So that's just generic, but let's look at some that have numbers and symbols and things. So here is an example. This is silicon. So here's the example. Okay. So the element is silicon, right? So Si is the symbol for silicon. Silicon, if we looked on the periodic table, is element 14. So it has an atomic number of 14, which would also tell us that it has 14 protons and 14 electrons. Now the mass number right here is 29. You can see here, the mass number is 29. Now mass number equals the protons, which we know is 14, plus the neutrons. So if we want to discover how many neutrons are in this particular isotope, we can take the mass number, which is A, minus the atomic number, which is Z, and that will always give you the number of neutrons. So why don't you can pause the video here and just read through again on this example and make sure you understand what's going where. And then we're going to practice some, look at some other examples just to make sure that you're getting it. But you can pause here and make sure you understand. All right. So let's practice. So it says an element has an atomic number of 20. How many protons and electrons are in this atom? Okay, so we want to use information that we've gotten on the last several slides. Pause the video and then try to answer it, and then I'm going to answer it. All right, so looking at this, the atomic number is equal to the number of protons. Okay, so I know it's 20 protons. And then I also know that the protons in an atom equal the number of electrons in an atom. So if it has 20 protons, then it must have, oops, I was going to write protons again. It must have 20 electrons. So 20 and 20. So if you answered letter A, then you are correct. All right, so let's try, and on any of these slides, if you have difficulty or have a question, feel free to reach out to me. Just refer to this slide about what you have a question, and I'll be happy to go over it. So let's try another one. Okay, so again, pause it. You read through it. You try to answer the question, and then I'm going to go through it, and you can match and see if you're getting it. Okay, so go ahead and pause it and try. All right, so it says an element has 9 protons and 10 neutrons in the neutral atom. When they say neutral atom in the problem, they're telling you that protons equal electrons, but I just want you to know, even if it doesn't say neutral, like let's just say this said an element has 9 protons and 10 neutrons in the atom. If they're calling it an atom, they don't have to tell you it's neutral. Atoms are neutral. We call things that are not neutral ions. And so if they say atom without the word neutral, don't use that as a stumbling block. Okay, so letter A. How many electrons are present? Okay, so I know protons equal electrons, so this is 9 protons. It is 9 protons, but it's also 9 electrons. What is the atomic number of this element? Okay, so protons, the number of protons equals the atomic number. So the atomic number is also 9. What is the mass number of this element? Okay, so mass number equals protons plus neutrons. So for this example, it would be 9 protons plus 10 neutrons, so that would be 19, the mass number. Then it says write the atomic notation of this element. Okay, so you would have to have a periodic table for this, and I'll skip back to my periodic table in the back of this show so that we can look at it together, but you would have to have a periodic table, and you will be given a periodic table on the exam. We can talk about more specifics, but in fact, I think the one I have in this slide is the one that you're given, or this video. Okay, so let's look. Atomic notation. So all right. So let's look. So I can tell 2 things just from what we have here. So I can tell, and okay, so my video paused. I don't know how long it paused, so I hope there wasn't a big gap in my talking. I don't have a way to go back and tell. That's another disadvantage of this. So let's just pick up. You can see here we have 9 electrons. We have an atomic number of 9 and a mass number of 19. So atomic notation, we put the mass number on top, so that would be 19. We should put the atomic number on the bottom, that would be 9. Now, you have to have a periodic table unless you've memorized it, which I don't require, because we need to look for element number 9 to know what symbol that this would be. So let's go back. Let's go and go to the end of the video, or the slides anyway. Okay, and we would look for element number 9, which is fluorine. And I'm looking at that little 9 right there. So this is fluorine. Okay, so let's go back. Let's see. Okay, whoops, sorry. Okay, so this is fluorine. Sorry for the craziness on the video. All right, so this would be atomic notation, or what they call the isotope symbol. Okay, so let's see the next one. So this, the next slide talks about isotopes. This is really just going to be an extension of what we've been working on. The definition of an isotope, or these are atoms of the same element, so they have the same number of protons, but they have different mass numbers. They have different numbers of neutrons. So if you recall, in one of the things that Dalton, which is, remember, 1800s, early 1800s, said, is that all atoms of the same element are identical. But once they discovered the subatomic particles, and they also discovered at the time of the neutrons, in fact, I think it's one of the reasons the neutrons were discovered, is that different atoms of the same element can have different masses. And the reason they have different masses is because they can have different numbers of neutrons. And so I have 3 carbon, and you don't have to memorize all the different isotopes. You just need to be aware that elements can have different isotopes. And so here's an example of carbon. So one way that they can tell you something is an isotope, or what isotope it is, I should rephrase that, is that they will put a dash and then a number behind it. And that number is the mass number. So remember, mass numbers help us know how many neutrons there are, because mass numbers are protons, which would be always the same for the same element, plus the number of neutrons. And the neutrons can vary. So for carbon, there's 3 different isotopes. There's carbon 12, and that's not a minus sign again, right? It's just a dash. But when we say the name, we don't say carbon dash 12, we just say carbon 12, carbon 13, and carbon 14. And these isotopes are not in the same abundance. In fact, carbon 12 is the more abundant of the 3, but they do all exist. Why don't we go ahead while we're here? Let's try to write the atomic notation of these 3 isotopes of carbon. And if you want to practice, just pause and you go ahead and write them. Then you can unpause and I'll work on it. All right, so they're all carbon. So the symbol for carbon is C. So they would all have a C. Carbon is element number 6. If you have a periodic table near you, you can look and see it's element number 6. I'm not going to skip to the back right now because it's just a lot of skipping, but carbon has an atomic number of 6. It's element number 6. And you don't have to memorize that. You'll always have a periodic table, whether you're working your homework, you can use a periodic table, or when you're doing exams. So this part is all the same for all of the isotopes. What's different is their mass numbers. So this would have a 12, this one would have a 13, and this one would have a 14. Now, what's interesting, and one of the reasons that they might not have discovered the idea of isotopes till, little in the early 1900s, but not one of the first things they discovered, is that chemically these carbon atoms act the same. So they'll do the same type of chemical reactions. Now, carbon-14 is radioactive, but isotopes behave the same way chemically as each other. So until they could discover that there were different carbons with different masses, they may not have noticed the differences, the variation, because the carbon was acting the same. In fact, they use a lot of radioactive isotopes in medicine. In part, they act the same way in our body as the non-radioactive isotopes, but when it's a radioactive isotope, then it gives off radioactivity, which then machines can detect, and they use that oftentimes like to create a picture of your body, things like that, an inside of your body, I guess I should say. All right, so let's look. One other thing I want you to do, and you can pause if you want and then do it and then see if you got the right answer. But if you were given a symbol or a name, so the name, the symbol, I'd want you to be able to tell me how many subatomic particles were in that particular isotope. So, and you can pause at any time to just you try yourself without me going through it with you. But like I would look, the first one, carbon-12, has 6 protons. In fact, all of these have 6 protons, right? Because they're all carbon. Carbon has an atomic number of 6, so all of them have 6 protons. And then we also know that for an atom, protons and electrons are equal, so each one of these all have 6 electrons. And then finally is the mass number. The neutrons, which involve the mass number. So to find the number of neutrons, you have to take the mass number, which is always going to be a bigger number. You can't, than the atomic number. You can't have negative neutrons. But you take the mass number and you subtract the atomic number. So you're subtracting the number of protons. So for carbon-12, it's 12 minus 6. So then that's 6 neutrons. So it's 12 minus 6. And then carbon-13 is going to be 7. Right? 7 neutrons because it's 13 minus 6, because carbon-13 has a mass number of 13. And then this is 8, which is 14 minus 6. So you can see here with isotopes, that's the definition of isotopes. They're atoms of the same element that have different numbers of neutrons in their nucleus. So carbon has 3 isotopes, and carbon-12 is just one of the 3 isotopes. All right, so I think I have some slides that we can practice this as well. So you can pause it and then try to answer. You will need a periodic table. Okay, so go ahead and pause. And it says, how many protons, electrons, and neutrons does sodium-23 have? Okay, so they're giving us here the mass number. So we have sodium. Okay, so we're going to find the protons on the periodic table. Sodium is Na, so you do, and it's one I want you to memorize. So let's look on the periodic table. I am going to bounce forward. All right, sodium is Na. There it is, right there. So it's number 11. So sodium has an atomic number of 11, has 11 protons. Sorry, I have to do this. Okay, so 11 protons. And then it also has 11 electrons because protons, electrons are equal. And then if it has a mass number of 23, we'd say 23 minus 11 equals 12 neutrons. Okay, so we got the number of protons by knowing it was sodium and looking at the periodic table. We know protons and electrons equal each other, and if you take the mass number, which was given in this problem, and subtract the number of protons or the atomic number, you get the number of neutrons. Now, I might also encourage you at this point to continue checking yourself and to go ahead and write the atomic notation, or what we also call the isotope notation. You can pause. I'm going to go ahead and write it, but you can pause if you want to try it first, which I encourage you to do. All right, so the atomic notation, Na is the symbol for sodium, so we would write Na. The top number, which is the mass number, is going to be 23. And then the bottom number, which is the atomic number, is going to be 11. In the atomic notation, the larger number is always written on the top. The mass number is always larger than the atomic number. Now, again, one thing I ask you to do in this chapter is be able to navigate between the name, like the sodium-23, the different number of subatomic particles, and the isotope notation. So given any piece of this, you should be able to navigate between those three pieces of information. So here's another one. Now this is written a little different because now it's using the symbols, not the names. So it's using Z and A. Okay, so go ahead and try to answer. This one's multiple choice. You go ahead, and then I'm going to ask you to try to write the atomic notation. So go ahead and try to do that too. All right, so this says how many protons, electrons, and neutrons are in the element with Z17 and A35. Okay, so one thing you have to remember to answer this question is that Z is the atomic number, and that's the number of protons. And so that is 17. So right away, I know it cannot be those two answers because I know I have 17 protons. Okay, then I also know if you have 17 protons, I have 17 electrons. That really doesn't help me in this multiple choice question because both letters C and D have that. Now, A is the mass number. It's not the number of neutrons, but I can figure it out from the mass number. So if I take the number of neutrons is going to equal the mass number, which is, I'll just write A, minus the atomic number, which is Z. So A is 35, and this is 17, so it's 18. So if you answered letter D, you are correct. So there's 18. So you do have to have that thought process. And if you feel like, oh, I can't do it yet, just practice more. I think if you can't do it, it's just because in your brain it's not coming easily. Like A is the mass number and Z is the atomic number. Like it's just not there yet. It just takes practice, some time. Let's go ahead and write the isotope or the atomic notation. So I know the mass number is 35 and the atomic number is 17. In order to finish this, I would have to go to my periodic table and find number 17, which is right there, which is chlorine. So see how it's number 17? So the element there is chlorine. So this question did not ask for the atomic notation, but I'm just trying to keep us practicing. Like the more we practice, the better we get. Okay, I think I have one more practice before the last concept in this video, which is kind of a long video. Sorry it's so long. So this says, write the atomic notation for an element with 24 protons and 28 neutrons. Okay, you can try, give it a pause and try. I'm going to keep working. All right, so 24 protons, that's my atomic number. That's going to tell me what element it is. It's going to be the bottom number. Now the mass number equals protons plus neutrons, so that's 24 plus 28, which if I add that together, 8 and 4 is 12, 52. So I can, from this question without a periodic table, I can get the mass number and the atomic number, but I've got to go and look at number 24 to figure out what symbol it is. So there it is right there. Chromium is number 24, so we're going to put the symbol Cr. All right, so that's that question. Okay, so the last thing we're going to look at in this chapter, and let me just pause again, because it's been a long video. If you're still hanging in there, that's good. Just practice this. Maybe write some of the definitions on flashcards so it just becomes of how you're thinking of it. But you can get this with practice. It's not a concept thing. This is really about knowing the language and what words go with what and where we would find them. So it's not concept. We're not having to solve a problem per se, but it does matter on the definitions and if you know where to find them and how they go together. So that it just takes practice. So the last thing we're going to do is talk about atomic mass that we find on the periodic table. And we're going to do one problem given all the information to show you how they figure out these atomic masses on the periodic table. So atomic mass or atomic weight is what we call a weighted average. Now, oftentimes things are calculated as a weighted average. If I ask you what an average is, like just an average, let's say if I had three numbers, if I took, If I took A plus B plus C and I divided it by 3, that is an average, but it's not weighted. Because when you take this type of average, which is commonly used, it's not a bad way to do average, but it takes all the values A, B, and C and makes them equal. Well, what happened is, remember you have isotopes, so let's just go back to carbon. Carbon has 3 isotopes. Those 3 isotopes have different masses. So now you're going to write a mass on the periodic table, and what do you do? And so I guess you could just write the mass of the one that is the heaviest, or write the mass of the one that you have the most of, or add them all together like a regular average and divide by how many you have. Well, none of those were what they did. What they did is they said, no, we're going to take into account how much of each isotope there is. And so if there's 80% of carbon-12, which I think there's more like 90+%, but I'm just making up numbers because we don't have to memorize it. Let's say there's 80% of carbon-12, 15% of carbon-13, and 5% of carbon-14, we're going to take into account how much we have of each. So the carbon-12 is going to count more than the carbon-14. And they used actual percentages, not just random ones that I could easily add in my head. So they did this, and then that was the mass that they put on the periodic table. And this periodic table, although it's teeny tiny to see, you can see here, these are all the masses, the weighted average of that particular isotope or that particular element. And we will use in a future chapter these numbers all the time. So they are important numbers for us. Now in this chapter, what we're going to do is I'm going to show you how this is calculated. Not so that every time you need an atomic mass, you're going to go and calculate it. You're going to go to the periodic table. But so that you can have a better understanding what this mass is representing. Okay, it's representing all of the isotopes in what we call, again, a weighted average. So how much they're found in nature. Which then makes me wonder, so if we go to the moon and they have different averages on the moon, or if we go to a different planet, like how does that change the periodic table? Just wanting to know for a friend. Okay. So here would be a problem that we're going to calculate. And in full disclosure, I usually have you do one of these calculations on the exam and show me how you go through it. But it's not something that we're going to do a lot in future chapters. I just want you to have some understanding of how the numbers come about. You will need a calculator for this if you have it. I already got my calculator. It's sitting right here next to me. And hopefully I won't plug numbers in wrong, because then sometimes I don't know. If you see numbers wrong in a video, usually it's because I did something in my calculator wrong. All right, so it says silver exists as two isotopes, and you're thinking, I know it's silver, I can just look it up on the periodic table, which is true, but we're going to see how they calculate it. Silver exists as two isotopes with atomic masses of 106.9041. Okay, 106, I'm just writing it down, 0.9041. This is in atomic mass units. And then I have a second one, which is 108.9047. Now, I want to tell you something really cool. Some of you, I don't know, you can think it's cool or not. So silver is Ag. The mass of this one is it's almost 107. So this is silver 107. That's its mass number. I can tell that because remember, the two particles that make up the mass in an atom are the protons and the neutrons, no electrons. So that if I see the mass is 106.9, I know that has a mass number of 107. And this silver, if it has a mass of 108.9, this is silver 109. Whoops. I don't know why. I must have hit something. Let me get that. 109. Now, here's another little side that's cool, and I shouldn't be going on sides when the video's so long. But, so you might think, well, why is it less? They're always less. Like, they're never more. Like, the mass of the isotope is always less, just slightly from the mass number. And so I was reading about it, and there's two reasons that it is less. One is that, and has decimals. Mass number never has decimals because it's protons plus neutrons. There's no decimals. But a mass will have decimals. One, it's measured. So we know from our measurement lab, like you're limited by whatever you're measuring with. You're going to have decimals. That's one. And then two, I was reading that, okay, so when matter was created, Einstein E equals mc squared. So the energy required for the creation of atoms, actually that energy requires that little m in Einstein's E equals mc squared. It requires a little bit of mass. So in the formation, a little bit of mass is lost. I just read that. So I don't know enough about physics to know, but it makes sense to me. So anyway, just a side note. So those are the masses which were given. Then it says determine the average atomic mass for silver if the percent abundance is, and they give me, I'm going to write this, they give me 51.82%. and 48.18%. Okay, now, so this is how we're going to do it. And in previous videos, I've written it all in a really long line, but I want to try writing it one on top of the other and see if it will help you. So what you're going to do, so to find the average mass, what you do is you take the mass, and I'm just going to put it for M of the first one, and you multiply it by the percent that it has of the first one over 100. So it's a percent, so we're going to change it to a decimal form. And then you add that to the mass of the second one. Whoops, that's not plus. Times that percentage over 100. And if you had a third one, you take the mass of the third isotope and you take its percent over 100. And then you add up those numbers all together. So what you do is you take the mass and multiply it by the percent in decimal form. And you do that for every isotope you have, and then you get your answer. Now okay, so this would have to be divided by 100 because I need it in decimal form. All right, so let me get an answer here. So, and you don't have to organize it this way. It does have to be done this way, but it's not organized. Times 0.5182. And I get this one, 55.3977. I'm going to leave those digits there for now. I'll tell you how I'll round them. and this is 108.9047. So I'm doing the mass times 0.4818. Oops, I did something wrong. That would have given me the wrong number. Actually, on this one, I'm going to know if I did it wrong because we're going to compare our answer. Okay, I get 52.4703. I didn't write all the digits, but I think I have enough. All right. So those are the answers I get for there. And then, so that's like I did this and I did this up here on the top, and now I'm going to add them together. Okay, so I did that, and now I'm going to add these together, because that's what you do. You take the mass times its percent in decimal and then add it together. Plus 55. So I'm adding the two together. And I get 107.8673. But that doesn't make sense. Oh, you know what I didn't do? Let me do something again, because on my calculator I didn't round, and so it's going to look a little different. Oops, sorry. So when I wrote exactly what I had in, this is what I get. Okay, so this is what I get. So this is the answer here. Now let's talk about rounding, and then we're going to check our answer. That's the weighted average. Okay. I didn't have three masses here, so I only did it twice. So now in terms of significant figures, this can be really annoying on this particular problem, because we have adding and we have adding and multiplication. So when I multiply two things, I would use the least. So this has 1, 2, 3, 4, 5, 6, 7 sig figs, and this has 1, 2, 3, 4. So when I multiply, I would round off to here. This one too has 7, and this has 4. So when I multiply, I would round to here. Now, when you add, you don't do total significant figures. You do how many, the most precise. So in this case, you can think of how many places past the decimal. And both of these go 2 past the decimal. So I'm going to keep 1, 2, and I'm going to round there. So the answer I want to report to you is 107.87 AMU, and this is for silver. All right, so we're going to check our answer on the next slide, and then we'll come back to this. So silver is right here. You see it's 107.87. Now this periodic table that I provided has, for most things, 2 past the decimal. Not everything, but most things it goes 2 past the decimal, which is what I prefer. Periodic tables can vary. That's not a requirement. But this one does go 2 past, so that's why it has 2 past. So we got the right answer. So we know we did this right. That's the nice thing about it. We did it right. Luckily, we don't have to do it all the time. So I went through it pretty quickly, but take a look at it again. If you're having more trouble, I can practice another one with you. But remember, you're given all the information to plug in. And what you're plugging in is into this equation up here. And this problem did not have 3. It only had 2, so I just did it twice. If I had 5, I'd have to do this 5 times and add up all the answers together. All right, so if you made it through the video, great job. You've been very patient, even if you took lots of breaks in between. But we'll keep going with chapter 4 in a different video. For now, we're going to stop here with this information about the atom.